So they are estimating height of average Indian male. Okay, so A is using a data. Okay, A is using sample size of 30. B is using sample size of 50. So B is using sample size, so or N. I will say N of B is 50, N of A is 30. Okay, and both have estimated the mean of the sample mean. The mean of the sample mean both have got as 1.65. Okay, create a 95% confidence interval for A and B. 95% confidence interval for A and B, that means 95% confidence interval for population mean, okay, by A and B, estimated by A and B. So that means what type of confidence interval these guys will come up. Okay, so for A, what we will do is confidence interval for A will be whatever the mean he has estimated. Here whatever his estimation is, okay, let's say his estimation we denote it as mu A plus minus Z into sigma by root n. Okay, n of A. And one thing we have to know is the standard deviation. So standard deviation, if population standard deviation is given, it is okay. If sample standard deviation is given, you have to take the sample standard deviation. Assume the sample standard deviation for this guy SA is 20%. SA is, let's say we are saying that the sample standard deviation for SA is 0.2 meter. Okay, the sample standard deviation for B is, typically B will result in a lower, okay, 0.15 meter. Okay, but the mean that they have got is same. Okay, so we have to find out the confidence interval of A. Can I say the confidence interval of A will be mu of A? What is the mu of A? 1.65. okay, plus minus, what is the value of Z for 95%? What will be it? Can I say it will be 1.96? It will be 1.96 into standard deviation. This guy has 0.2. Okay, divided by, let's say rather than 30 we take as 36. Okay, so we have root of 36. So the confidence interval for A will be 1.65 plus minus 1.96 into 0.2 by 6. Okay, and you can compute this, how much it will come as. So it will come as 1.65 plus minus 1.96 into 0.2 by 6. Okay, so and as per Mr. Ibrahim it comes as 0.65. Will it come as 0.65? I doubt. It is 0.9, so 0.392. Okay, it is 0.392 by 6, so it will be 0.065. Okay, it will be 0.065. So it will be 1.65 plus minus 0.065. So it will be 1.715, and on the left side it will be 1.585. So it will be between 1.585 to 1.715. Okay, and for the B it will be 1.65 plus minus 1.96 into 0.15. Okay, divided by, let's say he is not 50, 49. Okay, so root of 49 is 7. Okay, again you will compute this. Now what you will find is this is roughly how much? 0.2. Okay, so this is lower, or will it be higher? Okay, this will be lower than this. So what will happen is the confidence interval for this guy will be lower. If you compute 1.96 into 0.15 divided by 7, okay, you are getting is 0.042. So you are getting 0.042. Okay, so it will be yes. So what you have got is 1.65 plus minus 0.042. So it is 1.692 and 1.608. So what is happening is this B's confidence interval range is lower with the same probability. So B has done better estimation. So what we can say is increase in sample size will result in lower confidence interval, and which is better. So we are saying that the probability is increasing. Okay, so this is a method. So in the examination you might be asked to compute the confidence interval. The formula for confidence interval is point estimate, that is your whatever you have estimated as a mean, this is the mean of the sample mean, reliability factor z, standard error sigma by root n. Okay. Point estimate reliability is 0. Okay. Create an interval around the value will come from the probability or confidence. So this z value, remember you have to remember 1.65, 1.96. Okay, these are the two you have to remember. This with 90% probability, this with 95% probability. Okay. Reliability factor, it is a number based on the assumed distribution. Standard error, it is providing the, it is the error of the sample statistics, that is the error of the distribution that you have got. Okay, it is the error of that distribution. Okay. Now let us understand another distribution. Okay, and it is known as T distribution. Okay. Remember, like when we did this central limit theorem, we said we were stressing on the point that the sample size should be greater than or equal to 30, and that sample size greater than or equal to 30, we were saying that it is a good estimate for large sample size, and the distribution will be a normal distribution. Okay, that means the sampling of the sample mean, the distribution of the sample means will be a normal distribution. Now what if you take n less than 30? If you take n less than 30, the distribution of the sampling the distribution of the sample mean is not a normal distribution, but what it takes a shape is, the shape it takes is T distribution. Okay. So what is a T distribution? Okay, T distribution is similar to normal distribution, but it is not a normal distribution. Okay, it is symmetrical. Okay, it is symmetrical. Okay, it is symmetrical. That means the mean of the distribution, it divides it into two equal parts. So what we have is, we have T distribution. Okay, we have, this is a T distribution, and you have T distribution, the mean of T, it divides it into two equal parts. Okay, but there is one thing which is very unique about the T distribution. It has fatter tail. Okay, it has fatter tail, but it also has lesser height than normal. So it has fatter tail than normal, and it has lesser height than normal. Remember that when we did the kurtosis, we said that a leptokurtic distribution will have fatter tail, and that leptokurtic distribution had higher height. Here what I am saying is, T distribution has lesser height and it has fatter tail than a normal distribution. So if, let us try to create this. Okay, so it is it is a combination of lepto and platy. So what you have is, assume that this is your normal distribution. Okay, you can have a distribution, okay, which is a T distribution as this. Okay, it has a fatter tail, but its height is lower. Okay, so this is one T distribution. Okay, now what happens is, the sample size has a big role to play. Sample size has big role. Okay, why? We have said that if n is less than 30, it is a T distribution. If I say n is greater than 30, then we had said that we can take a normal distribution. Okay, so what happens is, in a T distribution, okay, this is, let's say n equal to 10. The blue one is n equal to 10. Okay, let's say we take another distribution. Okay, let's say orange one. Okay, and the orange one has, okay, has a height which is more than the blue one, and the fatness of the tail is lower. Okay, so what can be said about the n of orange one? Can I say that n of orange one will be less than 10, or can I say it will be more than 10? What it will be? What is happening is, if you see this orange one has lesser fatness, and it is coming near this normal distribution. We have said that the normal distribution, if it will become, when n is infinity. So the pink color, it will become when n is very large. Ideally, in reality it is infinite, but ideally we see that greater than 30 it will become. So what happens is, as n increases, okay, the peakness increases, the fatness of the tail, it decreases, and the t distribution is kind of becoming a normal distribution. So as n is increasing, t distribution is kind of trying to achieve a normal distribution. As at n equal to infinity, t will become equal to z. So t will become equal to z distribution when n is infinity. So what happens is, for a t distribution, it is very important that we know what is n. Okay, that is, we know what is the sample size, because the t distribution is kind of distributing the sample, distributing those having lower sample size. So we have to understand the sample size. So what we have a concept, okay, of over here is a concept of degree of freedom. The concept of degree of freedom, it says that degree of freedom is 1 minus the sample size. Okay, so for a t distribution, we have, this is important, that is degree of freedom. So entirely degree of freedom, if you see, what we do is, like, once mean is known to you, okay, you can only change the variables in one lesser way. So that is why we call as degree of freedom as n minus 1. That is the number of freedoms you have, the number of variables in which you can freely change those will be n minus 1. Okay, so as of now, just remember that degree of freedom is sample size minus 1, and as your degree of freedom increases, the t distribution will become more peaked and it will become lesser fatter. The tails will become less fat. So what we say is, degree of freedom is equal to n minus 1. N is the sample size. It has fatter tails than normal distribution. As degree of freedom or n increases, it assumes it approaches normal distribution. So if you see, this orange has degree of freedom of 1, this has 2, 5, and degree of freedom infinite, it becomes a normal distribution. Okay, it is useful if you are distributing sample size less than 30. Okay, now what we will do is, we will first try to understand the table of t distribution before we can go into anything. So we have to understand the table, how it comes. Okay, so what you have is, this is an example of a t distribution table. Okay, so what over here they have given to you, okay, there are like 2-3 things that we have to keep in mind. Okay, here they have given you tail probability. So unlike the way you had z distribution, okay, in the z distribution, what you had done was, okay, in the z distribution, we were getting the probability was, we were getting in the table. Okay, the inside the value we are saying z, and the probability which was output. Here what you say is, you specify the probability straightforward. So you will say that, okay, this is the probability. Okay, so what we are trying to come over here is, let's say this is a t distribution. Okay, we are saying that, assume as of now everything is two tail. Okay, so we are saying that distribution is two tail. We want to find out 95%. Okay, we are saying that inside this is 95%. So this plus this will be how much? So this will be 2.5%. Okay, this will be 2.5%. Okay, so if you see over here, what is the probability of this one tail? The probability of this one tail is 2.5%. Okay, now when one tail has 2.5%, what is the probability of two tails? When one tail has 2.5%, two tail means you combine these two. When one tail has 2.5%, what is the probability of two tail? Can I say 5%? So over here, if you see, whatever the value you get for one tail, the value that you get, the same thing for two tail. Okay, so whatever these values will be given, okay, it is, so whatever the one tail, just multiply it with 2, you should get the two tail. Why? Because that is how it comes. We are saying that this tail has a probability of 2.5. This means this tail also has a probability of 2.5. 2.5 plus 2.5 is 5%. So when one tail has a probability of 2.5%, two tail has a probability of 5%. Okay, now what we are trying to come over here is, okay, we are trying to come to know that, okay, let's say this is 90%. Okay, What is the one tail probability? If this is 90%, what is the one tail probability? Can I say it will be 5%? 5%. So what will happen is we will look into either one tail as 5% or combined tail it is 10%. We'll look into that. Okay. Now for the t distribution we need to know the sample size. As a result we need to know the degree of freedom. If you see over here this row, okay, you have degree of freedom. So degree of freedom 20, 21 like that it is given. Okay. Now if the sample size is let's say 30, assume the sample size is 30, what is the degree of freedom? 29. Or let's say over here, let's say the sample size is 20, what is the degree of freedom? 19. So sample size is 20, but we will not look at this, we will rather look at degree of freedom which is 19. Okay, the probability is 0.05, so we will look at 1.729. So this has a t distribution having a mean of 0. Okay, standard deviation anything we do not worry. Okay, so what we say is if the mean is 0, standard deviation I do not have to worry about it. When the degree of freedom is 19, this value will be how much? 1.729. This value will be how much? Minus 1.729. Okay. If it were a normal distribution, what was this value? Quick question. If this were a normal distribution, this value instead of 1.729, what it would have become? 1.65, right? So this will be minus 1.65. So what is happening over here? If you see this, okay, this is our normal distribution, okay, and this is 1.65 minus 1.65. We are getting the probability as 5%. Okay, and we have another distribution which is a fatter distribution. So this fatter distribution is like this. Okay, 5% will come over here or here. So can I say that 5% will come this side? Okay, because what is happening is it has a fatter tail. We will realize 5% over here rather than over here because this is fatter. So what will happen is the fatter tail, this number should have been lesser than 1.6965 and it is coming as 1.729. Okay, this is what we are getting. Okay, and as if you see this 1.729, as the degree of freedom is increasing, it is kind of decreasing. 725, 721, you are going over here. The fatness is decreasing. Okay, now no doubt if you take the degree of freedom as very high, okay, what you have taken is degree of freedom you have taken is very high. Okay, if you see the degree of freedom you have taken as 200, the value comes very close to 1.65. And many tables you will find that they give you the degree of freedom as infinite. There you will get as 1.65. Okay, in reality that distribution should be used only when degree of freedom is infinite. Okay, we are saying that for the greater than 30 Z can be used because error is very low. Error is very low, that Z can be used. Okay, but what we will be going through is we will be going through when to use T, when to use Z. Okay, so this is one concept that we have to remember, when to use T and when to use Z. Okay, yes, let's take this till over here. I want to get the values, okay, over here. Okay, when you want to know 95%, okay, when the degree of when the sample size is 15. Okay, when the sample size is 15, okay, I want to find out the 95% confidence interval, okay, of a mean. Okay, I am trying to predict the mean, but the sample size I have taken is only 15. Okay, and we will take the same data for the sample size we have taken as 15. The height we had predicted was 1.65 is the sample average. Okay, the sample size we have taken is 15. Okay, the standard deviation of the sample that we have got is, assuming that the standard deviation of the sample we got is 30%. The standard deviation of the, because when you take typically sample size low, the standard deviation comes higher. Okay, give me the confidence interval, okay, of population mean. Okay, question is clear? the sample size is 15. Okay, give me the confidence interval of population mean. Because the sample size is less than 30, okay, I cannot use a Z distribution over here. If I use a Z distribution, okay, what will happen is I will get error. Okay, the things will not be correct. So what we do is, we rather than taking a Z distribution, I use a T distribution. For T distribution, I need to use the T values. Okay, so again the formula for confidence interval will be the same over here, that is mu plus minus, rather than Z it will be T into S by root N. Okay, what is mean over here? 1.65. Okay, I'm sorry, I have taken as 30, it should percent. Let's take as 0.3 meter. Okay, it makes sense. S is 0.3 meter. So this is 1.65 plus minus S is known to me 0.3 meter. Okay, N is known to me root of 15. But what about T? We have to find out the T value. I am getting a confidence interval of 95%. So can I say that the one tail probability will be how much? 2.5%. Or I can say the two tail combined probability will be 5%. So I have to look into this particular table only. And what is the degree of freedom? Degree of freedom will be 14. So I will be looking into 2.145. Okay. So the value of T that I will take is 2.145. So 1.65 plus minus 0.3 by root 15 into 2.145. This will give you a value. And you find that this confidence interval range will be more. Okay, because what happens is, here your N is lesser, as a result this is higher. Here your standard deviation is also more. Okay, you can also take a comparison when by changing this N, okay, and not changing the standard deviation, you will find that confidence interval will be changing. Okay, if this were not a T distribution, if we had used Z distribution, this instead of 2.14 we would have taken as 1.96. So this is the issue with T. T will create a wider interval. Okay, please note that here we are computing confidence interval. Okay, confidence interval, in that what you do is you try to create an interval. So you have mean. Okay, you can go left side, you can go right side. Okay, as a result what we do is we have two tail. Okay, it is not that always we will be seeing two tail. We will be seeing, when we do hypothesis testing, we will be seeing one tail. Okay, and that is important for us to know, because one tail is important test that we have to understand. Okay, but as of now, for confidence interval, we have to use all the time confidence interval it comes, you have to think from the two tail perspective. Okay, in examination they will not give you table, they will give you just a snapshot of the table. Okay, in that they can either omit this entirely, they will just give you one tail. So you have to think that when they have given one tail, if you are want two tail thing, it will be multiple. Okay, or they can just eliminate this and they can give you only for two tail. Okay, so it is on their basis, like, but you have to have an understanding of both. And if they will not give you a table, they will just give you a snapshot. Okay, they will just give you a snapshot. So just to think about a person who does not know about degree of freedom, for sample size n equal to 15, they will give you this. Okay, they will give you 14, okay, 15 and 16. So some people may think that they have to take n as 15, so a degree of freedom as 15. Some people will make it correctly. Some people will forget that it is n minus 1 and think it is n plus 1. So these are the values which are given. Now when to use which? Okay, so when I should use Z, when I should use T. Okay, it depends on how you are sampling. So when to use which test? Okay, so this is what you have. Okay, we will solve that problem also. Okay, so what is the selection criteria for test statistics? What we say is it depends on from where you are sampling. Okay, if the underlying distribution is a normal distribution, okay, if the underlying distribution is a normal distribution and you know the population variance, okay, underlying is normal, you know the population variance, okay, it doesn't matter, okay, whether the sample size is small or sample size is big. Okay, you can use Z. Okay. So As per the central limit theorem, we said that, right? So for Z, it should be less than greater than 30. But if the normal distribution you are sampling from is normal, that means the population already is normal. Okay, that population standard deviation, the population is following a normal distribution, and what you have is the population standard deviation is known or variance is known. It doesn't matter, you will use Z. Okay. However, if the sampling, the underlying distribution is normal but the population variance is not known, okay, the population variance is not known, okay, what we will say is for a small sample size you use T. Okay. For large sample size you can use T or Z both. Okay. But what we say is, okay, when the population variance is unknown, okay, using Z is giving some error, more error. So T is more reliable. So this I have put star. Z can be used, but T is more reliable and conservative. Okay. So that's why Ali, you said that N maximum we want is 30, but the table was still 200. It is because of this, because when the sampling is normal, population variance is not known, you can use T for larger also. Okay. When the distribution is non-normal, okay, please, and I will give you a trick to understand. When the population distribution is non-normal, okay, please note that when N is less than 30, you cannot use anything. Okay. When it is not normal, the central limit theorem is not applicable for sampling size of less than 30. Okay. Okay. For less than greater than 30, it is applicable. Okay. When the population variance is known, you use Z. When it is unknown, you use T. Okay. So a quick way to remember this is whenever the population variance is known, okay, whenever the population variance is known, I will use Z or I will not use. Okay. You will not use when N is less than 30 and non-normal. Otherwise, every time it will be Z. Okay. When the population variance is unknown, I will use T, okay, or I will not have anything. You will not have anything when the population variance is not known. So this is what you have to remember. Okay. You have to use this. Okay. And you have to see the T distribution value, okay, from the table. So you want a 95% confidence interval, okay, for average score of the student. The number of students in the sample is 36, okay, and okay, this is, yes, number of students in the sample is 36. The standard deviation of the population is not given, it is given for sample. The population variance is not known to you. Okay. The average score is 55, okay. The standard deviation of the sample is 12. Okay, so what you have is, here you do not know the population standard deviation. So when you do not know the population standard deviation, we will use T will give us a better number. Okay. So what I have done is I have computed over here using Z as well as using T. It comes out that T gives a better measure. So 95% confidence interval. So first you will find out the standard error. Standard error is given as S by root N. S is 12, root N is 6, 36 root. So root of 36 is 6. So your standard error is 2, and you have to create mu plus minus Z sigma by root N. So Z, so 95% Z is known as 1.96 if you do this. Okay. But if you want to find out T, so for degree of freedom here is 35. Okay. So what you will be doing is, you will see the degree of freedom is 35. So we'll say that, okay, whatever the degree of freedom is 35. Please note that degree of freedom 35 is not given. So we can select 36 or 30, whatever. So here let's select 34. Okay. So which is 2.032. So we'll say we'll select 2.032. Okay, and use that value to compute the confidence interval. Okay. So this is how you will compute the confidence interval. Okay. Please don't forget to remember this selection criteria, which one to select, when to select T, when to select Z. Okay, so what I have done is, like, if you see from this aim, okay, we have computed a lot of things over here. Okay, sample mean, least square, T statistics, confidence interval, properties of point estimator. Okay, what is remaining is our concept of hypothesis testing. Okay, over here what you have is sample variance, sample standard deviation. Okay, this is statistics part. Okay, we will see that we have seen that sample variance we will do it by dividing by n minus 1. Okay, rather than dividing by the population total n, we divide by n minus 1. Standard error is known to me. Okay, confidence interval of the population mean is known to me. Okay, so what we will be doing is, so they have given like this very haphazardly. Okay, we have covariance and correlation for sample we have to compute. So next class will do hypothesis testing. Please note that this is very important class, and try not to skip that. Okay, in this we'll be understanding all of these things. So I remember like Ali asked about this thing. He said that alpha is error. He mentioned that alpha is error. Okay, what exactly is alpha? Alpha is given as 1 minus your confidence level. When your confidence level is 95%, your error is 5%. So we will be covering that when we cover this type 1, type 2 error, etc. Okay. Once we have done the basics of this hypothesis testing, okay, we'll start with linear regression. Okay, this linear regression will be done, and what will happen is, you see the 2 chapters, they are only for the confidence hypothesis testing for the regression. So next class we'll complete hypothesis testing, we'll understand the regression. Okay, and after that we'll be able to complete this hypothesis testing, very simple. Okay, in that same class we'll be able to cover the multiple regression, because it is just building on whatever we have understood in the simple regression. Okay, or this I could have covered in 1 day too, but what I do is, like, if I do it in 2 different days, I will ask you question and you will remember.